So today we are going to continue on with our work in systems of differential equations, just looking at a special case of what we're going to call linear systems of differential equations. So don't forget, you've got homework assignment due this evening, and then the next homework assignment is open, and that will be due next Monday. Just a couple of other announcements. You should have seen that your grades, your exam grades have been posted, and you can check them out in Canvas. Just be sure that if it's not clear how you were graded on each question, there's a little button that says show rubric that'll show how much points you earned on each question. And in the comments section, I uploaded an annotated version of your exam, so you can kind of see some of the comments in that PDF file. I just found it easier to annotate outside of Canvas and then upload it back in. But if you do have any questions or comments about it, just let me know. I'll just say, like, overall, I think it was a pretty good result. I think the average was about a 77%. And then I added 2 points on to everybody for that bonus of doing the survey. But if you do have any concerns about things, please let me know. And kind of relating to that, I don't know how well it's been advertised or explained to all of you, but there is another modified grading policy. Like in the spring, we had this P plus P NP grading policy. And they're doing something similar, but not the same this semester. So if you do want to adjust your grading from a letter grade to this modified grading, you have until Sunday, I think, to do it. October 25th is the deadline. So if you do want to do that, it's a form you need to fill out online and send in to CLAS advising. There's nobody that needs to approve it or sign it. So if you have any questions about that, that's something we can talk about outside of our meeting time. Okay, so any questions?
Did have a question about the quiz we just took.
Yeah.
I saw one on there that I'm confused about what the answer is supposed to be.
So this was like with matrix multiplication or something? Yeah, okay. Right. Let's maybe we can hold off on that until we get to the part today when we actually do some multiplication, and we can make sure that that looks okay. Yeah. Yeah, so as you might have inferred from that assignment, there is definitely going to be some connections that we take a look at now with linear algebra solving these systems. Yes, so I'm happy to talk about that. I'll just hold off for a moment. Anything else? Okay, so taking a look at worksheet 17, and so we've got two interconnected populations we can think about this now. And so we'll think about bacteria in two separate colonies. And I'll just say that these models are really, really powerful. This is how we model disease spread, by thinking about people, putting them into different populations, like the population of infected versus susceptible versus the population that have been vaccinated. And we treat these as three different populations, and we see how they interact with each other. So let's say we've got the following scenario here, where we've got the x dt is equal to 3x, dy dt is equal to minus 2y. And let's explain what's happening in this system between these two different colonies of bacteria, X and Y. So anybody have any comments to make about this system over here?
They don't depend on T.
They don't depend on T. That's right. So we're going to be dealing with autonomous systems. And that will certainly be the case for now. What else? Like, what's going to happen to population X as time goes on?
It is increasing.
It's going to increase, right? Indefinitely, because that derivative, if we assume x and y are positive, since we're dealing, or at least greater than or equal to 0, since we're dealing with populations, yeah, dx dt is positive, so that's going to increase. And in fact, every time t goes up by 1, we're basically tripling the population x. So this is kind of telling us that x is increasing by 3 times we can say each hour in this case is what t is measuring. And we kind of know how to solve these differential equations. And for the equation for y, we can see here that y will decrease. To 0. It'll approach 0 at least asymptotically. And here what we can see is every hour, it's decreasing by 1/2. So that kind of talks about this over here. How are these two populations interacting with each other? Are they competitive, cooperative? What's going on? Like if x is present, how does that affect y or vice versa?
They don't. They're independent of each other.
They don't, right? So there's no interconnection here at all. There's no y's that are appearing in the dx dt equation. There's no x that appears in the dy dt equation. So these two populations are not interconnected. So in some sense, it's not really a system of interconnected differential equations. We just have like two independent differential equations. And so we don't need any fancy methods to solve these. If I want to solve dx dt is equal to 3x, okay, we have various ways of doing this. We don't just want to integrate both sides. We can separate things. This is also linear and so on. And so here I think we would get that x is equal to some constant e to the 3t. And similarly, get something like this. And I should say that these two constants might be different, right? They would correspond to the initial population x and initial population y. All right, any questions? That was good. Okay, I like to just start from stuff that we've seen and move towards things that we haven't seen yet. Okay, so here, this is not really a system at all. This is stuff that we looked at earlier in the semester. So now let's kind of mix these populations up a little bit and see how this complicates things. So now we're adding an additional term right here that we didn't have in the previous system. So now there is some interaction here, and we don't really need to change what happens with our interpretation for y. So y is not going to be any different. It's still going to decay. It's still going to head to 0. We're still going to have the same solution. but X has changed now, right? And so what has changed with population X compared to the previous one?
Now also depends on why.
It depends on why. So what's happening now? So in the previous one, it didn't. So now X does depend on Y, and how so? Like as Y goes up, what would happen to X? Okay, what do you think, Rachel? What would happen to X if Y is present now, according to this differential equation? How does that affect X, population X?
It would increase it.
It would increase it. So the more Y that is around, we can see the larger dx dt gets. So the faster population X is increasing. So it's almost like Y is acting like a catalyst for X. And I think it's good to make these observations so that what the behavior that we see in our solutions will make sense. We won't get totally surprised by what we observe. Okay, so let's see. Over here, we had these solutions. And now what we're saying is this was the original. Oh, these are not the solutions, those are the equations, sorry. Here are the solutions. Okay, and so now we changed the system a little bit and we commented on that this stays the same. And so now if the equation looks like this, what would you expect the solution for X to be? It's going to have trig functions, exponential functions, some combination of both of those things. Brilliant. So any guess, Austin, for what this might look like? And there's something in the chat. Austin, same but divided by 10. So that it would look like something like that. That's one suggestion. Anybody think of something else?
I don't know what it would look like, but I think we could plug in the y equals c2 e to the -2 into dx dt.
We can, but we would still like to know, and we'll get some other differential equation there. We would get like a first order differential equation there. I'm trying to say, let's set this up for a guess and check sort of thing. So I'm going to come up with a guess. For x of t, and then I can plug in my solution for y, I can plug in my guess, and then actually figure out what x has to be. But this starts with what we practiced last time, which is how could we figure out what a good guess for this population would be? So let me just kind of back up. We looked at these individually when they didn't depend on each other, and we saw that x increases exponentially y decreases exponentially. And now we say, okay, let's interconnect x with y.
Would it be c e to the -2 and then a constant in front of it? Because if y is e to the -2, then we'd have dxt, and that would be e to the -2 too.
Yeah,
That would
so
have twos.
now that we know what y looks like over here, and we know that it comes up in this differential equation, it makes sense that we might expect this to appear in the solution for x. And since we still have this term over here in the equation, it makes sense that, yeah, we still should have some e to the 3t term over here where this constant might be different. That's right. So that's good. So both of those comments were exactly right. It makes sense that we might think this is going to look like e to the 3t plus some constant times e to the -2t. And we don't know what those coefficients a and b are. But we can find them out using like a guess and check method. So again, the point here is it's not a new concept that we've been doing this, trying to come up with, looking at the differential equation, come up with an educated guess and then check it. So now we can check this. Since we know what y is, we have a guess for x, then we can calculate the x dt. So that would be right, the derivative of our guess. And then we would take 3 times x plus 10 times y. And what's left is to just solve for these constants a and b. And what we'll see is that these constants are going to probably depend on what we had for C2. Sorry, this should be that should be at C2 over here. Any questions on what we're doing here?
So this looks okay as long as the one of them plays nice. It seems
Yeah.
like they're a little more difficult. This approach doesn't exactly work. Is that correct?
That's right. So we're taking our steps in that direction. That's right. So first we started with neither one of them depends on either one. Now let's just think about only one of them depends on the other, and then we'll think about what happens when we mix them all up together. Yeah, and so now it's algebra, right? So then we would kind of match up our e to the 3t terms Oops. So I've got one e to the 3t term over here, and I've got two e to the -2t terms over there.
I have a question.
Yep.
Why is like in the line right above the one that you just wrote down, why is that there a minus sign between the 3a e to the 3t and 2b e to the
Because we are taking the derivative of this.
Oh, okay, I see.
So that's
Yeah,
dx
okay.
dt.
Okay, I didn't follow that. Okay, cool.
And then from this, we would say, okay, if these two sides are going to be equal, well, then we need 3a to equal 3a, and we need minus 2b to equal 3b plus 10c2. And so from the top equation, we can see that a can be anything. And from the bottom equation, we could the goal here is to solve for A and B. We could solve this for B, and we would get that B is minus 2C2. So this gives us our solution for x. We just found that the term in front of the e to the 3t could be anything you want. The term in front of the minus 2t does depend somewhat on the initial setup for y. So that does make sense that depending on what our initial condition for y is, that's going to affect how fast x grows, and that's going to affect what x's population is. So there we just solved our first system that is somewhat interconnected. Our system would be solutions for both x and y. And then we can see again that this constant C2 appears in both of these equations, and that's because these populations are related to each other. Okay, any questions? So when things get a little bit more complicated, when they're all mixed up, it's going to be a little bit hard for us to start with like, what would my guess be for x, or what would my guess be for y? So like we did with the second order differential equations, we guessed that they should be exponential, and then we said the powers of the exponents, the r's, should satisfy some quadratic equation, and that's how we came up with our guesses. Going to be very similar process here. So let's think about the most general case, which would be given above. So this is what we would call a linear system with constant coefficients. Okay, linear because the x, the y, the x prime, the y prime all are appearing at most to the first power. And we're going to assume things are autonomous. So all these constants are constant. All these letters are constant. And building from the previous one and what we've been dealing with second order differential equations, our initial assumption is going to be, we're going to get some sum of two different exponents. And the question is, how could we figure out what the R1 and the R2 are? That was the whole trick with second order differential equations. And then once we know what those values are, we have like a general form to plug them into. So let me do some scratch work over here. And let me just say, you guys aren't going to have to prove this, but if you're curious about where do eigenvalues come up in this process, where does the linear algebra come up, I'll take us through that process. But again, this is kind of a means to a more simplified end eventually. So what I'd like to do is say, we're going to plug these conditions, my guesses for x and y, into these differential equations, and then see what the resulting conditions are on R1 and R2 to guarantee we have solutions. So the first thing we can do is just take the derivative of x, our guess for x, which is done right down here. And this should feel similar to what we did on the previous one. And then we're going to set the other side. So that gives us this part of the equation. And now we're going to calculate the right side of the equation. So we could plug in x and y. So I've got x plugged in green, if you can see that. And y is plugged in over here. And we have these general constants a and b. And just like we did on the previous one, then we group our terms together, like terms together. So I'm going to group my R1 and my R2s together down here. So I just distributed the A's and the B's, and then I had two terms that had an e to the R1t, and I have two terms that have an e to the R2t. And so then I set the stuff in front of the e to the R1t equal to the stuff in front of the e to the R1t. And this stuff has to equal the stuff in front of e to the R2t. So that gives us two resulting equations. And you know, for those that have taken linear algebra or are taking it now, we get a pretty nice linear system of equations. So it makes sense that there might be some way to frame this using matrices. But any questions about where those conditions came from? And then we could go through the same exact process using the equation for y, y prime. So I could take my guess for y, take its derivative, and then plug in x and y into the other equation. So my derivative would look like this. Left an r out. So I would have similar things, but now my constants are C3 and C4. And I'll just kind of take us through this rather quickly because it follows the same exact way. We would group our terms together, and then we get a similar system of conditions that R1 and R2 need to satisfy. And stuff is disappearing. So we get some conditions that R1 needs to satisfy. So I get one of these conditions from here, and the other condition on R comes from here. So if I pick out this one, and this one, that gives me this system of equations over here. And I get a similar one for R2. So in other words, it's a little bit more complicated. It's not a quadratic equation that I need to solve, but it's a linear system of two equations that I need to solve. And again, that's where the matrices will come in handy. So the question here is, how can we frame this using linear algebra? So on the one hand, I can take the R1 times C1, C3 and write it like that, right? And this would give me the vector RC1, RC3. Let's see. These got messed up, sorry. Right, those should be subscripts of 1 and 3 because that was coming from this equation over here. So I could take that equation up top, this system of two linear equations, and write it as a matrix equation. So I could write R1C1, R1C3 as R times the column vector C1, C3. And I can write the other side of the equation as a 2 by 2 matrix times the column vector C1, C3. And you can check that if you multiply this out, that you would indeed get AC1 plus BC3, and we would get CC1 plus DC3, which matches the equations that we wanted to get over here. Okay, are there any questions? Okay, so then let's just kind of back up for a second and let's just kind of review some essentials from linear algebra. So this is in section 3.2. There's actually more stuff in that section than we really need. What's really important for us is how to multiply matrices and how to calculate the determinant of a matrix, which I'm guessing you've either seen in a previous linear algebra class, or if you're in it right now, you've been working with that. So kind of the first thing is, right, we can multiply a scalar times a matrix. And to do that, we would just multiply every element of the matrix by that scalar. We can add matrices if we like, and then we can multiply matrices as well, where we would take each of these terms times each of these terms and sum them up. So there was a question on the reading quiz that kind of relates to this. So which was the question, Kyle?
It was actually question number 1. I have it up if you. It's a screen share.
I'll share it right here.
Perfect.
I've got it open too. So let's see. It's possible this was randomized a little bit. So which question?
The current one right there.
This one right here.
Correct.
Yeah, so if you multiply, this is exactly kind of what we were looking at on the previous one. So if you were to multiply this, you would take, I don't know if you can you see my pointer?
I can.
Yeah. So you would take the 3 times the x plus the 5 times the y, and that would give us this.
Where is that? Because
What's that?
that's 3x plus 5x.
Oh, I had a typo here.
Yeah, I also have
Yes.
on that one.
Okay,
Yeah.
I didn't see an actual answer when I was taking the quiz.
Okay, I will, I'll correct that, sorry. Yeah,
Thank
there
you.
was,
Okay.
I had a type, I meant to type y there, that's right. For this one, none of them are correct, yeah. Yeah, but to, what I meant to type was 3x plus 5y and then 6x minus 2y is what you should get, yeah. Okay, so yeah, that was the goal here, is that to go back and make sure everyone is familiar with multiplying this. Maybe I should have reviewed it myself. But any questions on how the mechanics of multiplying matrices goes? Okay, well then, let's come back to the worksheet then. Okay, so these are some terms that if it's been a while since you've thought about them, you might use them here. So we've got kind of zero vector, and we're mostly going to be dealing with square matrices. And when we're dealing with a system of 2 differential equations, that's going to be a 2 by 2 matrix. But what we commented back over here is that these conditions, we can write them in the following way. And if R satisfies this equation, this is by definition what it means to be an eigenvalue for the matrix, if you've seen that. So let me kind of just explain what that is, and then we can come back to the previous part. So we had an equation that was like exactly like this, except R vector V. So just so you know, like vectors are typically written in like thick or with an arrow above it. Since it's hard for me, I don't want to change the thickness of every time I write. I'm just going to use the arrow notation up top. So this V is a vector. In our case, this was like the C1 and the C3. And this value lambda, that's what we were calling R1 in the previous example. So we had an equation that was exactly R1, C1, C3 was equal to A, B, C, D. Times that. So it looks exactly like this form over here, again, where the V is C1, C3, and lambda, we usually use lambda to denote eigenvalues, is holding the place for R1. And so we do some arithmetic with matrices, namely, I can subtract this vector, because it's a vector from both sides, bring it over here. Then what's left over is just a zero vector over here. And then we can actually do some subtraction between these two matrices. And I can write this equation like this. And once we've got this vector in this form, we can see the only way I take a non-zero vector times some matrix and get the zero vector over here is going to be if this matrix has a determinant which is 0. So let's kind of just take a look at an example just to make sure we're comfortable with doing eigenvalues. Just to do some scratch work. And I'm going to just make up a matrix, so the eigenvalue might not work out particularly nice, but that's okay. Okay, so here's my matrix. And the question here is find the eigenvalues. Call this matrix A. So the way we do this, and this would be true whether I have a 2 by 2 matrix or a 20 by 20 matrix, is we subtract lambda, this eigenvalue, from each diagonal entry. And lambda is an unknown that we're going to solve for. And lambda is going to be really useful because it's going to tell us what powers we should use in our exponents in our solutions. So let me say step 2 would be to set up the characteristic equation. And the way we do that is we take the determinant of this matrix and we set it equal to 0, not the 0 vector, right? Because when we take the determinant of a matrix, we get a scalar number. And so when we take the determinant, at least for a 2x2 matrix, the calculation is a little bit easier. We just take the product of the two diagonal entries. And then we subtract the product of the off-diagonal entries. So it's kind of a three-step process. You know, first you've got your matrix, take the determinant of that matrix, and then solve the resulting equation for lambda. So this would give us like 18. What do we get here? Minus 9 lambda plus lambda squared plus 2. And we just witnessed a miracle here because this actually factors. I cannot believe that. That's probably the first time I've ever come up with a random matrix that has like integers as eigenvalues. Yeah, but now this factors into lambda minus 5 and lambda minus 4. So this matrix has these two eigenvalues, and let me just say that once we think about how we can set up this matrix from an initial problem, you can see that this is going to tell us exactly what these two powers would need to be in my solution. And that's going to be the power behind those. So rather than go through that long, drawn-out process that we kind of did to see where these equations come from, the nice thing is that those equations are, again, by definition, asking us to find the eigenvalues for that matrix. Any questions? Just kind of curious as who's seen eigenvalues in a course before? You can give me like a thumbs up if you have this one or a fake one. Okay. So some people have some haven't. So for those that are in differential equations, no, you're all in differential equations. For those that are in linear algebra, you'll be getting to that, I think, in about a week or so. So this might actually tie in pretty nicely to what's going on in that class. Okay, so then the question is, well, like, given a system of differential equations, how would we, what is this matrix A that we would come up with from the get-go? Because that's going to be our first step. Find the matrix and then go through this process that we just did. So I skipped over that, but if we kind of look back over here, the way that we can write this as a matrix equation is we usually use this vector, and notice that's in bold, to denote a vector of derivatives. So I could write this equation over here as, I'm going to say x1 prime, x2 prime, x3 prime, or you can write it just as above. And so the matrix we want to find is going to be the matrix of coefficients. So in this case, the corresponding matrix for this system of 3 linear equations would be a 4 and a 7 and a -1. So that would be the corresponding matrix for this system of differential equations. Since it's 3, we have a 3 by 3 matrix. That's one of the really nice things about this process, is that it scales up really, really nicely. It doesn't affect us very much. If you've got technology, then it's really fast to calculate eigenvalues, even if the matrices are large. And so just be careful when you're setting up these matrices that you know, the order might not be perfect. There might be some missing values, and you need to fill those in accordingly. But for your reading quiz, just so you know, for next class, it's not going to be anything new. It's just going to be things that I want to be sure you review before we meet on Wednesday. So that's going to be how do you set up matrices for this system, and how do you find eigenvalues? So it'll be, here's a matrix, tell me what the eigenvalues for that matrix are. So that's why this will be on the quiz. So was it clear what to do on this one? Let me see. Okay, and we can do this whether or not our matrix has constant coefficients. So here is an example of a non-autonomous system of differential equations, because now the coefficients have t in them, but it's still linear because x, y, and z's, they all appear at most to the power of 1. So if I'm working my matrix across this way, who's got a suggestion for what would go in the first place over here? I'll take some chats, whatever you guys prefer. Yeah, thank you. That's right. So cosine 2t over here. Same idea, just we might not have a number. These things might depend on t, but we're still going to say what comes in front of x, that's cosine of 2t. What comes in front of y, there is no y. And then over here, we have a sine of 2t in front of the z. Right, and here we have 0, e to the t, 0, and then sine of 2t, 0, cosine of 2t. Since we don't have constants there, finding the eigenvalue is going to be not quite a useful method here. But it does work for systems like this one above. Okay, so if we're comfortable with this, maybe a little bit less so with eigenvalues, but that's all we're going to need to solve these systems. So let's generalize this like we've been doing for like a more streamlined version. So if I were trying to solve this system up top without guessing and without going through the process of trying to guess, then step 1 is to set up this matrix A. And that comes from taking this system and just pulling off the coefficients, putting them, organizing them in the right spot. So this is what we're considering our matrix A. And just so you know, like sometimes people put parentheses around matrices, sometimes they use brackets. It does whatever you prefer to use. Okay, and then next we would determine the characteristic equation. So we're going to take the determinant of this matrix and set it equal to 0. So that's what we mean by the characteristic equation. Okay, and just for the sake of completeness here, that term is going to be 0, but I want to just put it there since oftentimes it's not. Okay, then we want to solve the characteristic equation. Thankfully, this one is already factored for us. And we've got two eigenvalues. It shouldn't be surprising that we saw these two eigenvalues. This was what we guessed when the first time we went through this problem. So that gives me a possible solution for x. And I want to just caution that we can't just say this. Since these two coefficients, they might depend on the values that we have for C1 and C2. In fact, they will depend on the values that we have for C1 and C2. So we don't just want to think about these as two independent solutions. So the constants depend on each other. So in order to figure out what y is, we can go back, for example, and use this differential equation to solve for y, since I know what x is already. So we can see, for example, I could bring the 3x to the other side, and then divide by 10, and that's going to tell me what y is, and now I know what x is, and therefore I could figure out what dx dt is. So for us, that would mean so that is our x prime term. And then what was the equation? It was 3x okay, so we can plug in dx dt, plug in 3x, and then just solve for y. I'm just going to bring all my terms to the other side, and what's left is minus 5 c2 e to the minus 2t equals 10y. So that would be my solution for y. And again, we found our solution for x over here. So what happens in this case is we find out that C3 actually has to be 0, and C4 in this case is minus 1/2 C2. And so you want to just be sure you don't keep all 4 constants general. After you solve this process, you should just have 2 general constants left in both of your equations, the same 2. Are there any questions on the process?
Yeah, so with what we just did, we're gonna find the general solutions of x and y. And then we're gonna realize that there's only gonna be 2 real constants. So we're gonna either take x or y, and we're gonna plug that into one of the original equations. And like we'll say x is the one we're gonna use. And then we take the derivative of x, and then we plug it into the dx dt equals 3x plus 10y. Then we solve for y with those 2 constants. Or we could take y and solve for dy dt if there was another one in y. Like it has to have x and y in each one. Is that right?
Yeah, it doesn't matter which way you go about it. You can first come up with, I get x is going to look like this, and then use that to figure out what y looks like, or vice versa. Yeah. You could do it either way. Sometimes there might be a slight advantage to doing it one way or the other. Sometimes it won't make a difference.
Okay. We find a general equation, and then we pick one of those x or y, and we plug them in to find the constants of the y, the other one.
Yep.
Okay.
And so this is laid out in section 3.4. So if you're kind of following the notes, let me just say this stuff, how we set up the matrix, this is in 3.3. That's a really short section. And then eigenvalues and how to use them come up in 3.4. And let me just say, the textbook doesn't quite use this last process. So they would say, we're going to find the eigenvalues, and then we're going to find the corresponding eigenvectors of each of those and use that information in the solution. I'll just say it gets really, really complicated when you have complex eigenvalues. So they say if you have real eigenvalues, you do it this way. If you have complex eigenvalues, here's a modified method. If you have repeated eigenvalues, then here's another modified method. The way I want to do it is just say, we're going to do this for all of those cases. We're going to only just have one method, and we can apply this method to all of those cases. And we're just going to circumvent eigenvectors. Okay, I need to stop and then come back since I think that froze. Okay, so I want to give you guys a chance to practice this. So before we do, are there any other questions? Okay, that one is not opening. Let me open it on my computer. Okay, so let's pick out 2 of these to practice in some breakout rooms. Then we can compare some results. So well, I guess it makes sense. Why don't we try A and B? Those are good ones to start with. So in your groups, I'll have you guys start with those. And one thing that I haven't talked about, what I want to do here is, what do you think we do if we get complex roots? So what happens if I say get lambda is equal to 3? This is a mess. Let's say I go through this process. Because you get quadratic equations, you might get complex roots. So I could get something like 3 plus or minus 2i. And if that happens, then what do you think our guess would be for x?
Don't you need like sines and cosines? Is that right?
Yeah, so we're not going to change any of that. And so I think that's what's nice, at least what I try to make nice about this method is it really is just going to draw in everything that we've done previously. So if you get something like this, that's where we would get these sorts of solutions. And that's what you would plug into the differential equation to then find y. And you'll see that y is going to have similar sorts of things. So it's the same process. It's just the calculus and the algebra get a little bit more difficult, but it's the same idea. And we do the same thing. If you had a repeated root, you would have C1 e to the RT plus C2t e to the RT. So we're just going to do the same thing that we did with second order differential equations. Okay, so let's take about 10 minutes to see how you guys are making out on parts A and B of 13. And rooms are open. So if you have some questions in your group, just put out the help signal. Otherwise, I will just check in periodically to see how you all are doing. Thanks. So let's just kind of check in on how you guys did with this, see if you had any questions. And we'll start next time working on some of these others that we didn't get to today. So we'll definitely talk about those and then move on and start to talk about the dynamics of these systems and whether these equilibrium are stable and unstable. So for this guy over here, part A, right, the process would be set up our matrix. Any questions where that came from? And then we set up the characteristic equation by subtracting lambda from these diagonal entries. So that's where this and this come in, and then taking the determinant and setting it equal to 0. Any questions with that? Okay, and then we can calculate the characteristic equation. So just so you know, sometimes that's often written with a p. So we'd say p of lambda, it's some function of lambda. And so if we distribute that out and group our terms, you should have gotten eigenvalues of -4 and 2, -2, excuse me. Any questions? Okay, and then from that, we could come up with a guess for x or for y. So we could plug these powers in, get our guess for x, and then we plug that into the other differential equation, and it becomes a bit of algebra. I think I left out of -1/4 over there. So this would be, when we give our general solution, we would want to give equations for both x and y. Again, yeah, we should expect that these constants over here are popping up down here. Okay, any questions? Okay, so you should definitely be able to get started on the homework. There's a couple of problems that are related to this, but before we talk on Wednesday, you've got that reading quiz, and I just want to make sure you're comfortable finding eigenvalues, because that's really the the new part of this process. The rest of it should feel pretty familiar. Okay, well, thanks everybody. Have a nice afternoon. If you have any questions, got office hours tomorrow, and otherwise don't forget you've got a homework assignment due this evening. Okay, have a nice afternoon, everyone.